Good evening all. Hope I'm audible and my screen is visible. Hi, good evening. Yeah, thank you. Okay, then I'll just start recording. Good evening all. Welcome to live session 5. And to give a brief discussion of overview of this course is mainly intended as a finite difference method for CFT, and also towards the end of the course we will discuss something called finite volume method. The basic idea is to solve the diffusion and eventually the Navier-Stokes equation. Intended audience are undergraduate and postgraduate students from mechanical and even other departments is also fine, as long as you are trying to solve the same set of equations. Basic prerequisites are the fundamental knowledge of mathematics and fluid mechanics should be sufficient for this course. At myself, I am a PMO scholar from Department of Mechanical Engineering, IIT Madras, and my research area lies in application of CFD techniques to understanding the thermal and fluid dynamics inside buildings. Regarding this session, we'll have this session every Saturday from 5 to 7 p.m. and links will be circulated through email to all the registered students. They can be accessed on YouTube, like all the sessions will be recorded and will be made available on YouTube and the Google Drive folder as well. And any questions regarding the course, you can raise them on the discussion forum. We're going into the Q&A here. And as I said, the recordings will be stored in the, like you will be accessing Google Sheet from the problem solving session recording here. And you can get all the course material that is being shared in these sessions as well as the recordings. Coming to the course contents, we started out with a brief recap of governing equations for the flow. And we classified different kinds of PDEs. After that, we discussed something called a finite difference method. And last week, we discussed how to apply this technique for elliptic equations. This week, we'll be covering parabolic equations. As a brief summary of the topics that are covered in the lecture videos, some examples of parabolic equations followed by two different schemes that will explicit and implicit schemes to solve this set of equations in the finite difference formulation, and some codes for 2D and 1D. Like in this session, we'll cover 1D codes, but 2D as well as 3D codes are discussed in the lecture videos, and previous problems to help those who are solving for examinations. Examples for parabolic equations are unsteady heat conduction equation. So the main theme for a parabolic equation is we have is any certain disturbance that has been introduced anywhere in the domain will be spread throughout the space, but along the time dimension, it will be like progressing only in one direction. So we have a sense of directionality to this, unlike elliptic equations where the disturbance will propagate everywhere simultaneously. In fluid mechanics, the example is the classic boundary layer problem. But in order to solve this, we have to know how to deal with this nonlinearity here, which we'll cover little later. Sorry. Oh, sorry. Okay. Okay. Yeah, as I was saying, for boundary layer flow, we need to know how to deal with these nonlinearities, which will not be covered currently, which we will take up little later. So for now, we will restrict ourselves to unsteady heat conduction equation. And we also discussed the concept of stability and consistency last week, which is something that we will take up more detail now, because in elliptic equations, that was not a big problem. But once we have the parabolic equation, we have a we have another variable time that is getting added in addition to the spatial variable. So whenever we use a solver, we need to make sure that as the solver progresses through it, the errors do not accumulate. So if I were to plot error as a function of time, so error is like whatever is your predicted from the numerical solution minus whatever is from your actual solution. This error as a function of time, if we would expect either it to reduce or become constant. Ideally, we would expect it to be keep on reducing, but even if it becomes constant, we will call it stable. If it keeps on increasing, then it is an unstable scheme. Consistency is another term where we say that it's the truncation error whenever we have a differential equation. So for example, when you have del u del x, which we've written as ui plus 1 plus the error that you would get here. This is called the truncation error. A consistent scheme is one in which the truncation error goes to 0 as the grid as well as the time step is also refined. So in this problems which we will have a time derivative and a space derivative. So we have an equation like this. So when we convert this into a finite difference equation, in that equation, whatever the residual terms that you are having here, those terms should go to 0 as both the grid and time step are refined. Then we call it a consistent scheme. So when we have a stable and consistent, like a scheme that is stable as well as consistent, then convergence is guaranteed. So the first step in these methods is explicit methods. So whenever, so if you have any governing equation of this is like a diffuse unsteady heat conduction equation where Phi is your time temperature, then it is basically unsteady heat conduction. So this is your thermal diffusivity. So the first scheme that is discussed in lecture videos is forward time and central space. So the idea here is in forward time, we have n+1, the superfix is my time coordinate and the subscript is my space coordinate. So I'll have a grid along the space direction and let's say this is my time direction. So what we know whenever we are doing this is called time marching method. So we would assume that we have the boundary conditions along with this. So which is usually like you will be specific. You need to know what is the value of phi at throughout the domain at a t equal to 0 has to be specified. And then we also have the boundary conditions. Say for a 1D problem, in this particular case, we have at x equal to 0, we need to know something about it. And similarly at x equal to the other end, we need to know something about it. If the phi value is directly given, it will be Dirichlet condition or whichever is the boundary condition. So we need to know the information at the boundaries and also we need to know throughout the domain what is happening at t equal to 0. So the idea behind explicit methods, you start with a given time. So at t equal to 0, let's say this is my t equal to 0. You know the entire values of phi. So all these values are known to us. And we have to just use this equation to find the value of phi n+1. So this is just direct substitution. This is second order in space and first order in time. But the problem with this is something called stability, which as I said just before. So if I were to just simplify this a little here, let's say I just have one coordinate. So this would become something like phi n+1. Let's say the i+1 and i-1 are not present here. So this is what we will be having if for suppose phi +1 and phi -1 are kind of, or otherwise I can keep this as a constant. So as you can see, this term is at phi1, I can write this as phi1 is phi0 times some constant plus some b, if we neglect b for now. Similarly, at next time step phi2 is phi1 times a, which is basically phi0 times a square. So as you keep doing this, n+1 will be a power n phi0. So as I said, if we need the scheme to be stable, we need to be having this a value to be less than 1. If this a value is positive, like greater than 1 and positive, then as the exponential of n will keep on increasing, and which means the value of a will keep on increasing as the time increases, and it will not be stable. So yeah, for example, if you are modeling an explosion problem or something where that kind of things are acceptable, that is a different problem. But in the problems that we usually deal with, where phi is not continuously growing, like it eventually reaches a stagnation point, or not a stagnation, eventually it reaches some stable value, then we need to choose a scheme such that the value of a is less than 1. So like the modulus of this is less than 1. That will give us a restriction on the value of delta t that we can possibly take for a given value of delta x. Of course, this is kind of a very rudimentary. There are other analysis, other ways to do this more elegantly, which we will discuss in next week. Like week 7, we will discuss on something called von Neumann stability analysis, where we will do this in little more rigor for all the methods. The idea is basically to see that as you keep marching in time, the values do not increase unconditionally. And there are other schemes as well. The idea is to increase the order of accuracy in time and space. So one such scheme is Richardson method, where you use delta t square and delta x square. So the key difference here is whenever we go with higher order methods, we also need to make sure that in addition to accuracy, we also have stability. We will do this analysis a little later in week 7 and identify this is unconditionally unstable. So this first algorithm, we will call it conditionally stable because there is a certain restriction on the values of delta t and delta x that I can take, under which this scheme is stable. But in this scheme, there is no possible combination of delta t and delta x that I can take, so that in order to achieve a stable solution, which means I cannot use this in any algorithm where I will eventually get a convergence. And the other one is the Dufort-Frankel method. The idea is very similar here. The only difference is you replace this with n+1 coordinates. Again, this is stable, but the problem is this is an inconsistent scheme. This will also is again discussed in the lecture video. Or if you want to explore, all you have to do is do the Taylor series expansion for these terms and see what is happening with the terms of delta t and delta x as both of them go to 0. If in the limit both of these tending to 0, if you are able to recover back the original differential equation, then that particular scheme is called a consistent scheme, which the professor has already derived in the lecture video for this particular equation, for this particular form. It will not actually become 0. The residuals will not actually become 0. They will become indeterminate form. So you call this as an inconsistent scheme. To just get familiarized with the idea of how to evaluate this, let's take a small problem. So you have a thin plate with the initial at t equal to 0 as 200 Celsius. At a certain time, so this is the east coordinate and this is the west coordinate. So let's call this x equal to 0 and x equal to L. On the east coordinate, temperature is suddenly reduced to 0 degrees Celsius. And here we have an insulated one. The analytical solution is given to us. So all we have to do is write the finite difference equation form for this and then solve that. Just for simplicity, let's take 3 to 4 nodes. So in order to write the equations, so let's say the superscript is for the time index and the subscript is for space index. So for this coordinate, it is insulated. Let's start from the interior coordinates. For any interior node, we have the governing equation. So for T2, the equation would be using the explicit scheme. T3 is the I+1 coordinate minus 2 T2 plus the I-1 coordinate divided by delta x square. So as you can see, like initial temperature is already provided to us. So at all these points, initial temperature is 200. Since initial temperature is given, this let's say at n equal to 0, all these values are known to us. All we need to do is just calculate n+1 value. This is actually straightforward process. All we need to do is substitute the values of 200 here, plus alpha value, delta t and delta x square are given. The only thing is delta x is provided to us. So I have total length as 2 centimeter. So delta x is 0.02 by 5 and alpha is given. So with this delta x and alpha, we need to choose the value of delta t. So the criteria, as I said before, we are using a forward time central space scheme. So in this scheme, as we have seen, we need to have 1 minus 2 delta t by delta x. Modulus of this should be less than, should be less than or equal to 1. Let's take a strictly less than 1, or we can also take less than or equal to 1. So if we were to expand this, what we would eventually get is alpha delta t by delta x square is less than or equal to half. Delta t should be less than or equal to. So the key point here is delta t is less than or equal to something. So the maximum value of delta t that you can possibly take is limited by value of delta x. So as you keep refining your spatial mesh, the value of delta t will also get reduced further. So for example, in your particular problem, let's say you're solving a problem which is like, in order to get the desired level of accuracy, you have to use a very fine mesh. Say you are in kind of a region where you have boundary layer flow or something where delta x is very small. Like you need to be very close to the wall in order to resolve the boundary layer where there are steep gradients or something. So then you would have to use a very small delta x. So once you use a very small delta x, and if you are using a scheme like this, like a forward time scheme, then delta t also has to be very less. Otherwise, you would end up having stability issues. So for this case, you can substitute this and you would get a value of around 8 seconds. So I have to use a delta t less than or equal to 8 seconds, and then just substitute this to get t2. The only problem here is how do I get the values of t1n? Like initially I know t1n, but let's also do at the boundary nodes. Let's take the east node first. East boundary is straightforward. We have Dirichlet condition. So it says that the temperature of the east side is suddenly reduced to 0 degrees Celsius, and we are assuming that it is kept fixed at 0 degrees Celsius. So that is a straightforward one. So T5 is 0 always. So this we don't have to do anything. West boundary we have insulation. So now we have to write our scheme in such a way that we'll have to use that value. So which is del T del X should be equal to 0. So since this is second order accurate in space, we can simply use a first order scheme and say that del T del X at this particular point is T2 minus T1 by delta X at any given time step. Let's say n plus 1 step is what we are solving for, equals to 0. This gives us, this is the first order scheme. Or you can also use a second order scheme wherein this will become something like you use the Taylor table and then you can get the second order one. That would give you something like 3 2 plus 1. Sorry. So the boundary node comes first, minus the next node, and then we have the next node. This is a second order accurate scheme. And from this you can solve the value of T1. But as you can see here, when I'm calculating the value of T2 at n plus 1, I'm using T1 value at the previous time step. Like all these values are from the previous time steps. So when I'm updating the value of T2, it is actually seeing the boundary value of at the previous time step. Ideally, when we define parabolic PDEs in week 2, what is said is information actually spreads throughout, like any information or any disturbance that is propagating from the boundary will have to be, like every other node will actually see this disturbance. What is happening here is every node is actually seeing the disturbance, but the disturbance is kind of lagging by one step. From this we can get T1. So if I were to implement this as a code, what I would be doing is I would have to store the temperature, initial temperature in an array first, and then I will have to update all the interior nodes for one time step. So I'll have to put a loop for all the time steps. So for 0 to whatever time you want to integrate, first you will update interior nodes, and then you update boundaries, and you keep repeating. So as you can see, at any given point of time, all I'll be solving is for only one unknown, and that's why we call this method as an explicit method. Everything on the RHS is a known thing, and so we're just solving for this one. The only problem with this is there is a limitation on the value of delta t that I can take for any given value of delta x. So as I keep refining my mesh, I'll have to refine my delta t also in order to get a stable result, which may not always be acceptable. So then comes the other set of methods, which we have called implicit methods. So the only difference here is, while we were discussing previously, we said we will take all the values at the previous time step, but in the implicit method, we would be taking the spatial derivative at the future time step that we are solving for. So now all these values, sorry, this should be I plus 1, phi I plus 1, phi I minus 1, and phi I, all these are unknowns. So previously when I wrote the equation, there was only one unknown, and that is phi I n plus 1. Everything else is a known quantity. But in the current formulation, in the implicit formulation, we'll have, except for this, everything is an unknown. So what this results to in is we'll get a set of equations, and we have to solve all these equations simultaneously. So that is what we discussed in the elliptic equations when we were discussing TDME and other techniques. So all this results in is a matrix form, and on all we have to do is solve that matrix using direct method, or you can also solve them using iterative methods, whichever way you choose, and solve for that set of equations. But this is first order in time and second order in space. In order to get second order in time, so what we do is a small trick here where we split this into two time steps and solve, or you can also understand this as in a different way. Instead of solving directly for n plus 1, so this is the forward time scheme, this is the backward time scheme. So you take average of these two, and then you can use in this, or you can take different weightages also can be given. So if you are, which you will see later in any of the Crank-Nicolson method solvers, you will see like giving this weightage depends on how much stability you can actually get to. It's like always giving it completely, you can make this thing, let's say this is W1 times this one, W2 times this. You can, or I'll just write it as 1 minus W1. You can decide how much weightage you are going to give for the implicit or explicit solver, and then accordingly get to the manage your stability. And then you also have to deal with, let's say if you are using an iterative method in combination with this, like this results in set of simultaneous equations. So now we have to solve those set of simultaneous equations, for which we'll again use the relaxation techniques that we discussed last week to solve those equations. So if we take the same problem, just to understand how this can get transformed into the set of equations. So this is the same problem as before. How would the equations look like is, so let's start with interior nodes first. So unlike the previous one, now we'll have Ti plus 1 at n plus 1 and T1 n plus 1 by delta x square. So we'll just take all the known sides on one and unknowns on the other side. So that would give us 1 minus. So I'm just taking terms of T3 n plus 1 alpha delta T by delta x square. T2 n plus 1 and then T1 n plus 1. I'm just taking this term on to the RHS. So this is for one node, node 2. Similarly, I can write equations for node 3 and node 4. So let's just call this some R. This will be 1 plus 2R. This will be R. So if I were to write the same for node 3, so this will be T4 n plus 1. T3n. And similarly for node 4, we were to write n plus 1 is 5 for I plus 1, n plus 1 r minus 1 plus 2 r, the current node plus r times the node on the left side. So if you were to club all these equations together into one matrix form with the values as T2, T3n plus 1, T4n plus 1, and what if I were to take the coefficients together, the RHS is for the first equation, it is minus T2n minus T3n minus T4n. Yeah, sorry, have a question. Yeah, so if I were to club the coefficients together, so for T2 I have in the first equation I have minus 1 plus 2r, T3 is r, I do not have a term for T4. In the second equation for T2 I have r, for T3 I have 1 plus 2r, T4 I have r. In the third equation for T2 I do not have any term, T3 and T4. Now there are some terms left over here that we have to take care of. So we totally have 5 different nodes. So I will be having T1 and T5 also. So how do I accommodate them into this matrix? So at the boundaries, the treatment is again similar. So at the east boundary, we have a Dirichlet condition. So all we have to say is T5n plus 1. I have to expand this matrix also. So for the last equation, when we are writing for T4, we have a T5 term, that is this R. So we do not have any T1 term in this equation. We do not have any T5 term in this equation. Similarly here. And for the T1, T5, we have T5n plus 1 equals to 0. That is equation directly given from Dirichlet condition. So I do not have to solve for anything. So T1, T2, T3, T4, I do not have any coefficients. T5, I have the coefficient is 1 and that the RHS is 0. Now similarly, if I were to write an equation for the first node where I have insulation condition, that is del T del X equals to 0. This I will write it as, again we will use a second order scheme, or if let's say if you want to use a first order scheme, then it will be T1 n plus 1 equals T2 n plus 1. So this would just be written as 1. T1 coefficient is 1, T2 is minus 1, remaining everything is 0. Or you can also go with a second order scheme. If you so the equation remains the same, so it will be 3T1 n plus 1, T2 n plus 1, sorry, T2 n plus 1, and then we have T3 n plus 1 by 2 is the second order accurate scheme for the derivative del T del X equals to 0. So with this scheme, the coefficients for T1 is instead of 1 we have 3. Maybe I should round this. So instead of 1 I have 3. For T2 I have I just take 2 on the other side, so this will be minus 4. And for T3, I have 1. So depending on whichever scheme you use, you will appropriately populate that matrix first. And then all we have to do is solve the system of equations. This is basically Ax equal to B. And RHS is, for both of these cases, RHS is 0. So all we have to do now is solve this equation Ax equal to B, for which we have already discussed several methods. You can use iterative methods like Gauss-Seidel or Gauss-Jordan method, or you can also use direct methods. Say use Gaussian elimination or something that you already know how to solve this linear set of equations. So the advantage that we are going to get with this method is the delta t that we can actually take is actually higher, way higher compared to the delta t that you can take in the previous case. So when we discussed explicit methods, the limit on delta t is specified by the value of mesh size. But in implicit method, it will be stable. The only problem here is with the accuracy that you are going to get. Sorry, have any question? Yes. Hmm. Yes. So this one is particularly is the TDMA. We can directly solve with TDMA. Like we have this diagonal structure. Okay. Okay. I have not done on a GPU, but let's say I've done on multiple CPUs. If you want to do, you can use like how do you make it parallelized or something like that. I think we were discussing that last week also. Like you can actually parallelize this with Gauss-Jordan, but I do not have like you can vectorize this equation and then solve it. Like if you are using Python, I have not done on a GPU, but if you yes, yeah, there are separate books as well. Yeah, because as far as I've seen, at least I can tell from what I used, I've not used a GPU one, but the one basically all of these equations reduced to is something like this. It's a infinite volume or something. Even if it is unstructured, it is basically this one. All you're trying to do is you will know these coefficients, but these coefficients will not be some constants, where phi is a variable at the current index and this will be the neighboring point and p is some constant. And all you're doing is trying to solve this equation, right? So this set of equations we solve with using say Gauss-Seidel method, Gauss-Jordan method. Like last week when we were saying, we can solve this as you start with an initial guess throughout, and all you have to do is let me just write this as ppn plus 1 is some relaxation times whatever you are getting, and this pp star you can get from Gauss-Seidel. But as you were saying about parallel thing, instead of using Gauss-Seidel method, if I were to use say Gauss-Jordan method, where pp star is like pp and pp star is basically you just take a and b, phi and b star, and all of these are taken at the current iteration value only, and you store all of them in pp star, and this you can actually do in parallel, right? Yeah, all your but the memory is the only problem is you have to keep track of vp star and pp separately, but then you can actually parallelize this. I think this we can do easily in Python. Like the NumPy anyway has the vectorization, so all you have to do is just give this indices. Yeah, this is straightforward. This we discussed last week. Okay. Just a summary of all the methods in different accuracy schemes. Correct? Mm. Yeah. So the different schemes are like from the explicit, we have these three are the explicit schemes and their time accuracies. Out of this, the Richardson is unconditionally unstable, so this method is not practical. And then we have Clifford-Frankel scheme, though it might be stable, but then the problem is with the consistency, where consistency is like as the limit when delta t and delta x tends to 0, you need to ideally the truncation error should go to 0, but in this particular case, it becomes indeterminate. And then comes the implicit methods, where the backward time or the Crank-Nicolson, which depending on the order of spatial time accuracies, both are unconditionally stable. But again, as I was saying before, just because something is stable doesn't mean it is accurate. So, for example, ideally, like when you use the backward scheme in this implicit method, here we do not have any restriction on the delta t that I should take. So in this, there is no restriction on the delta t that I can take. For in this particular case, we have delta x equal to 0.004. So previously for explicit method, I have a limitation that delta t has to be less than or equal to 8 seconds. We do not have any such criteria for this particular problem, but that doesn't mean when I can use whatever delta t I can use. Like if I keep a delta t of say 8 or 10 or 20, depending on the problem you have, the solution you get might not be accurate for that particular delta t. So you might still have to reduce your delta t, but the limitation is not imposed because of the spatial grid, but it is because of the nature of the problem itself. Yeah. So these are some previous year questions. To those who want to appear for exams, you can gauge what the level of questions for this particular topics. Which of these governing equation is parabolic? So we have discussed this right away. But how do you do that? So when we take a differential equation of form, so when we have a PDE of this particular form, we have to calculate the discriminant, and depending on whether it is greater than, less than, or equal to 0, you identify which type of PDE it is. And for parabolic, we need that to be equal to 0. So which one of these is parabolic? The first one we discussed last week. So these are the steady state equations which are elliptic in nature. But sorry, C. Oh, you can just calculate and see. So for let's say for third option, we have utt minus c square uxx equal to 0. So we have, okay, I should have put something else here. Let's put capital. So b is 0, a is 1, c is minus c square. So b square minus 4ac is 4c square. It's positive. So this is hyperbolic. Now if you similarly do for the other equations, this doesn't have a second order at all. So a, b, c all are 0. And then what we have is this equation where you have a equals to 0 and, or let's say a equals to nu. If you are following this thing, y square is, there is no xy term, and then we have 1. So b and a are 0. So b square minus 4ac is 0. So this is parabolic. The only problem here is this equation is actually not linear. Okay, but here also if we take, we have b equal to 0, a equal to 0, c equals to 0. This is not second order actually. So we are not actually discussing this set of equations in this class, in these sessions. Okay, and which scheme is inconsistent when solving a 1D parabolic equation? This is more like a memory question. So the only scheme that is inconsistent that we discussed in this class is Clifford-Frankel equation. But even otherwise, how do you decide when a particular equation is consistent or not? Is you take the finite difference form of the equation and then write the Taylor series expansion. So let's say when we for this particular scheme, So this is the finite difference form equation for that particular scheme. So all we have to do is expand this equation with the Taylor series and then see what are the truncation error terms and keep and put the limit delta t delta x tends to 0. When you keep that limit, if the truncation terms are not becoming 0, then that particular scheme is inconsistent. Of course, in order to solve this particular question, you need to remember what is the finite difference equation for each of these names. So this is a little bit of more memory thing. Yeah, as I was saying previously, like when we have the Crank-Nicolson method, so we can also take something called beta, generalized beta method, where you give different weightages for both implicit as well as explicit parts of that equation. So if you see the Crank-Nicolson scheme, you can give a weightage for this. So depending on the weightage you give for the implicit and weightage for the explicit, you can eventually get to the value. The particular one, the Crank-Nicolson, is when the value of this weightage is equals to 1/2. This is also more like a memory thing. So just so that you know, you have to remember some things to get your certificate for the exam. Okay. What is the maximum grid step size that ensures a stable solution for 1D unsteady heat conduction using the forward time central space method? Alpha is given, delta x is given. Alpha delta b by delta x square should be less than or equal to. So this again we have to keep in mind. So this is a 1D problem. So we have 1/2. Depending on the problem, this will keep changing. If you have a 2D or a 3D problem, this might change. In general, you can, if you don't want to remember anything, you can derive the finite difference equation, and then we will discuss how to get this stability in week 7. There is something called Newman analysis, but the idea here is simple. So as you keep iterating as you keep marching in time, the value of the error should not increase, or the value should not keep on growing. So for this problem, you can just substitute these values. We have 5 into 10 power minus 6. Less than or equal to half. Basically 10 mm. So delta x should be greater than or equal to 10 mm, which means the minimum thing that you can take is, oh sorry, did I miss something? Delta x should be greater than or equal to 10 mm. As I said just now, I missed this in the summary part. So there is already another method, alternating direction implicit method. So the idea here is, so the one that we discussed previously is a 1D equation. We can also have a 2D form. So let's take this equation. So this equation is written in 1D. So now when I have a 2D equation, so it will be written as like I will be having one more term, gamma times del square phi del y square. So in 2D, in addition to this, I'll have two more terms where like in the subscript, I'll be having I plus 1j, ij, I minus 1j instead of the same thing again. And then I'll also have ij plus 1, ij and ij minus 1. And instead of delta x square, I'll be having delta y square term. So this will be the additional term that I will be getting in 2D. Now, in order to solve the 2D problem, so as we discussed, even in elliptic equations, you can do something called an alternate sweeping. So what we do there is instead of integrating directly from 0 to delta t, what we do is from 0 to delta t by 2, you'll write this equation, the same equation. So this will be instead of n plus 1, this will be n plus half. For this particular step, you will fix the x direction, or essentially you will solve using implicit method for delta x. So what I mean by saying implicit for delta x is all of these terms will be n plus 1, and for the y terms everything will be n. And from delta t by 2 to delta t, you will again use implicit for y but keep explicit for x. So all these n plus 1 will become n, and these values will become n plus 1 for the second half of the time step. And then you keep repeating this for like for one time step, you will be taking one sweep across y being implicit and one sweep across x for being implicit. Like you keep alternating this thing, and that is the ADI method. You can refer to the lecture video for the derivation of it. So the idea here is it is actually conditionally stable, and the stability criteria is 1.5. Okay. So once you write that equation, it will be very similar. The only difference is we'll be having three terms. So just like I have gamma x, I have alpha t delta t by delta x square, right? For 1D equation. So similarly, we'll have something along the other directions also. And the summation of this should be less than or equal to 3 by 2. The derivation of this is there in the lecture videos. You can go through that. If you have any questions, we can discuss on that also. But the methodology is very similar. So you just write the equations together, which will just be like in 1D it was just simple. Now we have to write for along y direction, along z direction, and then we have to club all the terms together, and then we'll see that this term being upcoming there, and then it will be less than or equal to some particular quantity. The math is involved, but the idea is intuition is straightforward. Okay. This is again a straightforward one. So all you have to do is take this term. We have rho Cp by kappa times, and this we would expand if we were to expand this in terms of space. It's just a mathematical manipulation by delta t, and then we have delta x square coming from the other side. So if I were to club the terms together, the coefficient alpha is here by kappa times delta t. So just the only problem here is you just get confused with alpha as being thermal diffusivity or something, and then you mess up with the options. Other than that, this is not anything else. So all you have to know is how to differentiate, like how to write the difference equation for in time and space, and just rearrange the terms. Algebraically, you have to just put the terms together, and then we get it. Okay, maybe this I'll ask you to solve. So let's say we have this equation del u del t minus del square u del x square equal to 0 with the truncation error. So when you write the Taylor series expansion for this and this, like I didn't mention which scheme we are using here. We are constructing our own scheme, and with that particular scheme, we got the truncation error as follows. So what will be the value of theta for which truncation error reduces to second order time and fourth order in space? How do I solve this? Yeah, you're saying something? Sorry, do you have something to say? So how do we solve this? The idea is to essentially only have this term and everything else in the to go to 0. So only then this error will reduce to that particular quantity. But how do I do that? So all I have to do is make this term equal to 0. This is 0. The order of accuracy for that particular finite difference scheme will be second order in time and fourth order in space. So how do I solve this? So we'll again assume that this particular scheme is going to be consistent. So we can start with ut equals to uxx. All we need to do is find the relation between these two variables, and I can write an algebraic equation entirely in terms of delta t and delta x. Then I can solve for theta directly from that. So this is again a bit of algebra, sorry, calculus, whatever you call it. So u2t is uxx t, and assuming that the function is continuous, differentiable, and all of that, so you can interchange these things. So u2t and this are equal, so I can just take them out. So if you can figure this out, the faster you get to the solution. I don't think there are any equations in this. Okay, this is again the equation that I told you before. So this is something of the form a u y y plus b u x y plus some c times u y y plus something equals to 0. So all we need to do is, for a parabolic equation, we need to know the discriminant is 0. We just substitute that here. And from this you can get the value of p. This we do not have here. For parabolic equation, it has to be equal to 0, so p will be equal to some value. Only thing is, you need to know that the discriminant is equals to 0 for a parabolic equation. And because the discriminant is 0, we are going to have one real characteristic line. So for hyperbolic equation, we'll have two solutions, so minus b plus or minus. So each one will be with different characteristic line. And for elliptic equations, the discriminant will be less than 0, so those will be imaginary characteristic lines. Okay, now let's some numerical problem. So this maybe you can solve one. So you can expect such questions in the exam. If someone is registering for exam, you might have to solve this one, like hand calculations. So we have a rod is 10 centimeter and delta x is given as 2 centimeters. So I have 0, 2, 4, 6, 8, and 10. Initially, the temperature is fixed as 100 at one end, 50 at the other end. Using forward time central space with delta x so and so and delta t 0.1 second, the temperature distance is 4 centimeters from the left end after 0.6 seconds. So this is 2 centimeters, this is 2 centimeters. So we are asked to find the temperature at this point at t equals to 0.2 seconds. So you have to do the iteration twice. So you write the same equation as before and then you can solve it. Maybe we can do this. Sorry. Sorry, if you do not have any questions, can you please unmute yourself? Sorry, can you please mute yourself? Yeah, if you do have any questions, you can unmute yourself. So how do we solve this? So we have the same equation as before. Maybe I'll show you some code so we can solve this. If you want to solve it with hand calculation, you can have to write the equation. So we are trying to solve for T3. So T3 at n plus 1, the difference equation will go as T3 at n by delta T is alpha times right side is T4n. We are using forward time. So it will be n minus 2 times T3 plus T2 times n by delta x square. Alpha, delta x, delta t, all these values are given. So at t equal to 0, or basically n equals to 0, I have t to be equals to initial temperature is 0 degrees Celsius. So I have t equal to 0 everywhere. At t equals to delta t is 0.1 second. So at 0.1 second, this will be n equals to 1. At 0.2 second, n equals to 2. So one key point here is, since we are solving a parabolic equation, the information from the boundary will be passed throughout the domain, which means I cannot just simply solve for this equation independent of every other node. I have to take into account the influence of other nodes also. So first I have to solve for n equals to 1. So take this equation for all the nodes, solve for n equal to 1, get the temperature values, and use those values to solve for n equals to 2. So this will be a two-step thing. If the question was asked at any other point, let's say the boundary point or something, then it would be straightforward. Here, since it is a Dirichlet condition, we do not have to solve for anything. So T1 is always 100 and T6 is always 50. So we are not solving for anything. If it was, say, the other condition, say there is no Neumann-Ernst condition, then we have to account for that accordingly. But otherwise, this is straightforward. So all you have to do is do this equation for multiple times and then we'll solve it. Maybe I'll show you some code. So implementing that will be a little straightforward. Start from the first problem. Hope my screen is visible. Can you see the code? Oh, okay. Yeah, I think now you can see my screen. So this is written in Julia, but which is kind of very close to MATLAB and open source. So just so that I don't want to give much into the programming logic as such, but the main idea of the pseudocode should be straightforward. So this is for the first problem that we discussed. So first let's solve this problem, Q10, question 10. So length is given as 10 centimeters, left side temperature is 100, right side is 50, and alpha is given as 0.835. All of them are in with respect to CGS units, so I did not convert anything. Delta x is given as 2 centimeters and delta t as 0.1 seconds. So first thing is you discretize your domain. So what this statement does is it creates an array such that x equals to 0 with the delta x 2, 4, 6, 8, and 10. So when you write 0, colon dx, colon L, what it will do is it will create an array of this particular fashion and then stores it into the variable x. So length nx will give you the length of that particular value. So we initialize the at t equal to 0, temperature is given to be 0 everywhere. So what this line does is it declares the entire domain to be zeros. Okay, there are 6 points. I should not write like this. And then we have our left and right coordinates. They're always constant. So just a second, I think some error. Sorry. Yeah. So left and right, we have the Dirichlet conditions. So T0 for the first node is going to be T left, and for the last node, it is going to be T right. And then we will define our new variable. This will be the value of temperature at the next time instant, Tn plus 1. So I'm calling that as T1. Is similar of T0. What it does is it creates an empty array, which is similar to T0. And then now comes the next step. This is where I was saying about parallelization. So what we can do is something called vectorization that is defaultly available in Python, NumPy, or in Julia, MATLAB, whatever it is that you are using. So what you can do is, instead of writing a for loop, we can also write this in a different way. So where we say, I can also write this as for, I have only two steps, t equal to 1 and 0.1 and 0.2. So I can write another loop for 1 to whatever coordinates I'm having as the t1 value at j for the interior nodes, so 2 to nx minus 1. I have to write this as the previous value plus alpha times delta t by delta x square times t0 of j plus 1 minus 2 times t0 of j plus t0 of j minus 1. This is what we would usually write. So the same equation And then this is for the interior nodes. Then comes the boundary nodes, where you define T1 of 1 is T left and T1 of right is T right. So this is one way of writing it, but then we have to go through the entire like one by one in a sequential way. If you want to make this parallel, what we can do is tell like this is internally handled by Julia language itself. So all we have to do is we have to just write these indices separately. So from 2 to n minus 1, so this will be my correct indices. So j will correspond to this value. So for j plus 1 will be, these values will be incremented by 1. So this will be 3 to nx. And similarly for j, again it's 2 to nx minus 1. And for j minus 1, these indices will be subtracted by minus 1. So it will be 1 to nx minus 2. So what this internally does is it kind of does it in parallel. And then we can, these are the boundary conditions. So this for loop is actually now replaced with one line. And this will be for kind of faster when you go for bigger systems. However, here it's not a big problem. And then what we have to do is update our current time step to the previous value. So the previous T0, T volt will be the whatever the value of T1 I'm going to get here. This is some notation thing in Julia where you keep dot equal to, which means you do an element by element thing. So people who are familiar with MATLAB will understand this better. So we have to iterate for 2 steps and then we'll get an answer like t equal to 0.1 and t equal to 0.2. That is what is asked in the problem. And you are asked to find at x equal to 4 centimeters. So this is 0 to 10. So 4 centimeters is the second, first, second, and third one. So T1 at 3. So I'm getting around 0.04357. 435 something. Now we'll also look at the other two problems. Yeah, this problem here. This when we were discussing, like I wrote the equations here for the implicit method and also for the explicit method. The same equations, you can also just quote them and see the effect of stability, etc. So let's say we will start with the explicit one. So these are the values. Length is 2 centimeters, conductivity is 10, rho Cp is 10 into 10 power 6, alpha is k by rho Cp. So I'm just taking 11 grid points. Dx is L by nx minus 1 because the spacing is just subtracted by 1. So delta t I'm considering as 0.5 times delta x square by alpha. So this is the one that is given from the criteria that we have. So delta t cannot be greater than this for explicit method. Nt is 120 by delta t. 120 is the total time that the problem asked us to solve for 120 seconds. So Nt will give you the number of time steps up until 120. What this does is it creates an array of size nx and fill everything with 200. So that is the initial condition that is given in the problem. So everything is kind of similar to whatever we did just now in the problem. But here I've replaced with the for loop instead of writing it as in a vectorized way. The only difference now comes is the insulated boundary. So in the previous problem, we have a Dirichlet condition. So all I have to do is say that temperature at that particular value is equal to the boundary conditions. Now when I have insulated condition, I have to modify this equation accordingly. So the equation becomes something of like this sort, where T1 is the first boundary cell at n plus 1 is, I'm using a second order accurate scheme. So this will be 4T2 n plus 1 minus T3 n plus 1 by 3. How do I get this? This we already derived in a few weeks back when we were discussing the Taylor table. You draw the Taylor table and then make the like depending on how many equations. So I'm considering 3 terms here. So I'll consider the first 3 terms of Taylor series and make the coefficients, all the other coefficients equal to 0. That will give me this one. So if you want to use more, you will get higher and higher accuracy as you keep on increasing more and more points. But now we will just stick with the second order accuracy because spatially it is second order accurate even in the interior nodes. So that gives me this equation. So first I'll calculate for the interior nodes what is the value of temperature for n plus 1 and use that value to update my boundary conditions. Once I updated the boundary, this is just to kind of log these values. The question asks me to find the values at 4 time steps. At 3, t equal to 40, t equal to 80, and t equal to 120 seconds. So all I have to do is log those values. And then I already have the analytical solution. Let's say for all problems you do not have this, but this is just a kind of checking to this function just gives me the analytical solution and then I'll compare these solutions. So for t equal to 40 versus 80 versus 120. I should have plotted all in one. Okay. But what I wanted to show here is, let's say this is the limiting criteria that the minimum time step that we got is 0.5 times delta x square by alpha. This is when we are using that one. Let's say if I increase this, what do you think will happen? So if I'm using a time step which is greater than the stability criteria dictates for this particular fully explicit scheme, then what we would expect it is it becomes it will not converge. If I try to run this, so these are the kind of solutions I'm getting. Here it is kind of oscillating, but eventually you can see that the amplitude of oscillation also keep increasing. This will just go erratic. Maybe if I can show you something lesser than that criteria, let's say 0.8 times something or 0.5 times the step, whatever the stability criteria dictates. You see it again, I was able to recover the solution. Of course, again, as I was saying, your delta t will not like for explicit methods, the maximum delta t that you can take is limited by the stability criteria. But now let's say if you want to move to implicit method, so here we can overcome such limitations. So when an implicit method, what we have done is we did it using a matrix. So first we'll have to populate the matrix, which I already have here. So this particular matrix we can populate and then solve for all of this in one go. That is what we do in an implicit method. So everything else remains the same. So only difference is we'll have to populate this matrix and then solve in one go. So this has some default function, just like MATLAB, it has this function that can take care of the solving part. Otherwise, we can write our own iterative solver. There are iterative solvers available also. So I'm not focusing on the solving part itself. But the point that I want to stress here is, if I've taken this, so the criteria for 2, when we solve with explicit method, we observe some kind of oscillations and the solution is not kind of converging. But let's say if I do the same with an implicit method, you can see that it is actually kind of matching even at a value greater than the stability criteria limits. So this method is implicit methods are actually stable and you can use much bigger delta t compared to what explicit method gives you. But the problem is they're stable, but let's say if I increase it further to 4 times whatever the stability criteria is, you can see that it is stable, it will give you a solution, it will not oscillate, but the accuracy becomes a problem. You might get a solution, but that solution is not accurate. So for implicit schemes, theoretically there is no limit on delta t as far as stability is concerned, but from an accuracy point of view, you have to choose your delta t accordingly. Are there any questions? Yeah, so these are the questions I have for this week. If you have anything to discuss, we can discuss. Or okay. I guess there are no questions. Yeah, yeah, these are the questions I have for this week. There are these 2D and 3D problems, but then there is no point in discussing them. Like it would be just an extension of this, and I'd have to just show the course, and then there wouldn't be any intuition as such. So I've not taken any 2D problems. Okay, then I think we can end the session for today. Thank you for joining. So next week we'll be discussing hyperbolic equations, and then comes the stability analysis. And with that, we'll start. After that, we'll start finite volume method. Okay. Thank you for joining. I'll end the session for today.